Okay, so the work that I'll present here is already available in the archive. It involves a group of people from the NSF CCI, which is led by Victor Batista. The name of this center is Center for Quantum Dynamics on Modular Quantum Devices. And I'm showing here the picture of the first three authors. Jorge Chavez and Thalia Lezama are postdocs working with me. I'm Lea Santos. Rodrigo Cortinez is a postdoc working with Michel Devoret. I'm also showing a picture of one Francisco Perez Bernal, who is one of our external collaborators. Okay, so this presentation will be divided into pieces, so you can watch each one of these pieces. Each one of these pieces will be a short video. So in this first one, in this first short video, I'll be talking about this term that appears in the title of the work, spectral kissing. So spectral kissing corresponds to the idea of excited state quantum phase transitions, or ESQPT for short. To explain what an ESQPT is, let me start talking about quantum phase transitions. Right? So quantum phase transition is a change that happens in the ground state of a system, an abrupt change that happens in this ground state as we vary a parameter of the Hamiltonian. And so it's a change that happens at zero temperature. There are different systems that present QPTs, quantum phase transitions, such as magnetic materials. So let's see an example. So I'm starting with this Hamiltonian. Sigmas here are Pauli matrices. So what we have in mind here is a lattice of spins half. And we have two competing terms in this Hamiltonian. G here is the control parameter. So when G is large, this term is important. What we have is a paramagnet, meaning these spins are pointing in random directions. Now, when G is zero, so we do not have this term, we do not have the transverse field, we only have the interaction in the Z direction, the ZZ interaction, which is the easy interaction, then we have some order in the system. Now, our spins will all be pointing down in the Z direction or up in the Z direction. And in this case, now we have a ferromagnet. Okay, very well. Here we have now a double degeneracy. So if we start on this side, if we look at the ground state, we'll see that this ground state is separated from the first excited state. But as we decrease the value of this control parameter going towards the ferromagnet, we'll see that we'll reach a point where this separation will vanish. And beyond this point, we'll have a doubly degenerate ground state. So this point where the gap vanishes corresponds to the critical point of this quantum phase transition. Let's see another example. Still kind of similar, we're still thinking about spin, but now instead of a lattice of spins half, we have just a single spin. So this SZ here is a sum of Pauli matrices in the X direction, or a sum of spin half operators. And so what we have now is a single spin, which has this size n/2. And again, we have two competing terms in this Hamiltonian. Xi here is our control parameter. So when Xi is zero, we do not have this term, we have just the Z term. The ground state of our system is this, the spin is pointing in the Z direction, pointing down in the Z direction. Now, when Xi is 1, so we don't have the Z term, we only have the X term, but this is Sx squared. Now our spin is pointing the X direction, but it's doubly degenerate. Now these two options are equal, no? We have the same energy. Okay, so if we look again at the energy of the ground state, when we are at this point, Xi0, the energy of the ground state is separated from the energy of the first excited state. As we now increase Xi towards Xi1, what we'll see is that we'll reach a point where this gap will vanish. This is the critical point for the ground state quantum phase transition. Beyond this point, we'll have this doubly degenerate ground state. For this model is known as Lipkin-Meshkov-Glick model. For this model, the critical point is point 2. This is the story of the ground state, but now we are going to look at the whole spectrum. So what we are seeing in this panel here is all of the eigenvalues of the system for different values of the control parameter Xi. This Hamiltonian conserves parity, which means depending on the value of mz, our state either belongs to the even parity sector or to the odd parity sector. So in this panel, I'm distinguishing these two sectors. Black lines correspond to the eigenvalues that are in the even parity, and the red dashed lines correspond to the eigenvalues that are in the odd parity sector. Okay, and well, let's again focus on the ground state. The first one is even, and the first excited state, which is odd. They are separated, but once we reach point 2, they merge together, the gap vanishes, and beyond this point, we have the degeneracy between this first excited state, which is odd, and then the ground state, which was even. Beyond this point 2, we have the double degeneracy. Now, this merging of adjacent levels happens not only here, it will happen also at higher energies, but then at a higher value of the control parameter. For example, for this control parameter 0.6, we'll see that the levels merge together, these pair levels merge together close to this energy around 0.4. Okay, so this line marks the point where these pairs of adjacent levels are getting together, are merging together. This line marks what we call excited state quantum phase transition. On this side, the X part of the Hamiltonian dominates. On this other side, the Z part of the Hamiltonian dominates. Okay, now this is what we are calling spectral kissing, the fact that the levels merge together. So this is a term that the group by Michel Deboré used in their experimental work, where they were analyzing the spectrum of a system that we'll be discussing here. So they used this word spectral kissing, and then we came with our theoretical work, which is the one I'm presenting here, to explain, well, spectral kissing is what is known as excited state quantum phase transition. Now, more important than this kissing, that the merging of the levels together, what we see is the following. We see an accumulation of levels along this line. This panel here, I selected just one sector. I'm showing here just the even sector. I could do the same just for the odd. And I'm showing just one level, just one sector, to show to you that something is still happening here. And is this accumulation, this clustering of eigenvalues that I told you. So if I pick a certain value of Xi, let's say Xi 0.6, and select all of these eigenvalues, and then look at a histogram. So we are looking now at the density of states. What are we going to see? A peak. And where is this peak showing up? At this energy, something very close to 0.4. This peak is what characterizes, is the main feature of the excited state quantum phase transition. This peak diverges as the system increases. Now, so what we call excited state quantum phase transition is the singularity in the spectrum. And the energy where we have this divergence is the energy of the ESQPT. For Xi 0.6 is around 0.4, as you can see here. For Xi 0.4 is something a little below 0.2, and you can see here, and so on. Okay. Now, there are different systems that present this ESQPT, this excited state quantum phase transition. We showed to you the Lipkin model, but there are some models also that are used to describe molecules, for example. And so on one side, the molecule has some properties, on the other side, it has other properties. Okay? But the special feature in systems where we have 1 degree of freedom, 1 effective degree of freedom, is this divergence in the spectrum. When we move to systems that have higher number of degrees of freedom, then it starts getting more difficult to see this feature. For example, if you think about the decay model, which is a model with 2 degrees of freedom, instead of seeing this divergence in the spectrum, you see it in the derivative of the spectrum, okay? But up to now, we then cover the first term of the title, spectral kissing, is the merging of this pair of adjacent levels that happens along this line of the ESQPT, excited state quantum phase transition. So this is the end of the first part of this presentation. Second part of the presentation will be about the last words of this title, the story about this Kerr-nonlinear oscillator. So I'm stopping here. This is the first part.